Hi, this is Captain Frank, and I'm going to be going over the last example problem dealing with the double integration method, which is found on block 3B note taker starting on page 14. This is the most complex example problem that we'll go through in class, and it involves a simply supported beam with a 7 kip-foot point load. So the first step for this problem would be to solve for the support reaction since they're not given. And by inspection, since there's a 7 kip-foot point moment in the middle, no matter where that moment is along this beam, it has to be countered by a 7 kip-foot clockwise moment. Given that the supports are 10 feet apart, we know that AY is equal to 0.7 kips up, and CY is equal to 0.7 kips down. That will produce the clockwise moment to counter that point moment. So the sum of moments anywhere on this beam will be equal to 0. By inspection also AX is equal to 0. The next step before we start integrating is to find the moment equation. Now because we're asked for the deflection and rotation at midspan, which is located at 5 feet, right about there, we have two choices to cut. We could cut between 0 and 4 feet or between 6 and 10 feet. Since we're concerned about solving for things at midspan, the smart thing to do first would be to cut somewhere between 4 and 10 feet, right about there. That way we'll be developing functions that are valid between 4 and 10 feet. So we'll draw a free body diagram, and I want to choose the right side of the cut. Even though we're cutting between 4 and 10 feet, we could still choose the left side or the right side. I want to start with my axis, draw my body, apply the 0.7 kip force down at C, show my cut there. V of X is going to be up, P of X is out of the cut, and M of X is drawn in that way, making the beam smile. We also need to label distances here. So as a rule of thumb, I like to label X starting at the far left end, which is off our free body, going to the cut, meaning that from the cut all the way to the right end is going to be 10 feet minus X. And I'll label this as point C. So we're going to sum moments about the cut and set that equal to 0. We'll get negative M of X minus 0.7 kips times 10 minus X equals 0. Therefore our moment function is equal to 0.7x minus 7 for 4 feet to x to 10 feet. Okay. Let's scroll down to get myself some more room. Once we have the moment function, we can start integrating. Slope is equal to 1 over EI, and we'll pull that out because it's a constant, times the integral of the moment function with respect to x. Therefore, it's going to be equal to 1 over EI times the integral of 0.7x minus 7, which is 1 over EI times 0.35x squared minus 7x plus C1. We're going to integrate again to get our function for y of x, which is displacement, and this is equal to the integral of what we just got, which was the slope with respect to x. So it'll be 1 over EI out in front times the integral of 0.35x squared minus 7x plus C1. And that's going to be 1 over EI times 0.117 x cubed minus 3.5x squared plus c1x plus c2. And just like our moment function was valid between 4 and 10 feet, so are these slope and deflection equations. So I'll write that down here so we keep that straight. It's very important. Now once we have our two expressions, one for rotation and one for deflection, as you notice we have two constants, c1 and c2. We need to solve for those. And we solve for our constants by identifying and applying boundary conditions. And that's what I'll start doing on the top of the next page. So we need to find out what our boundary conditions are. Between 4 feet and 10 feet, for boundary conditions, we have the deflection at 10 feet is equal to 0. And if I scroll up to look at our original picture, we know the deflection is going to be 0 at 10 feet because at 10 feet we have the roller support. And rollers, we can't have any vertical deflection. If we think about any other possible boundary conditions that are valid between 4 and 10 feet, there really aren't any. We don't know anything about slope. We know that at a roller support it will allow some kind of rotation, so we can't say that it's 0. It's not a symmetric loading case, so we don't know that slope is 0 at midspan. So this is kind of a point where we're stuck to some extent. Let's go back and try to get ourselves unstuck. So we can try applying what we know, which is this one single boundary condition. And let's see where that gets us. So if we plug in 10 feet for x and set that equal to 0 with the function that we just solved for at the bottom of the last page, we have 1 over EI times 0.117 times 10 cubed minus 3.5 times 10 squared plus 10 C1 plus C2 equals 0. We can multiply that through and we get 117 minus 350 plus 10C1 plus C2 equals 0. And therefore we can get about as far as this, 233, negative 233 plus 10C1 plus C2 is 0, and that's all. So there are no more boundary conditions and we don't have any continuity conditions. So we need to get ourselves unstuck by making a second cut that's valid between, and developing equations that are valid between 0 and 4 feet. So it seems a little counterintuitive because if we cut there and integrate twice, we're going to end up creating two more constants from integration, a C3 and a C4, but that's our only option at this point. So we'll start off by another free body diagram. This time we're looking at the left segment, and I'll choose to look at the left side of the cut. So this will be point A, 0.7 kips up. We're still going to call X from the far left side to our cut. V of X now goes down. P of X goes to the right, still out of the cut. And our moment, M of X, still makes the beam smile. Notice since I'm cutting between 0 and 4 feet, that point moment does not exist on this free body diagram. Again, we'll sum moments about the cut and set that equal to 0. Therefore I have M of X minus 0.7x equals 0. And so our moment function is 0.7x for 0 to x to 4 feet. Just like we did with the last segment, we're going to integrate that twice. The first integral will give us the rotation equation. So that is going to be 1 over EI times the integral of M of X d of X, since our EI is constant. and that's going to be 1 over EI times the integral of 0.7x with respect to x, which will be 1 over EI times 0.35x squared plus C3. The second integral is going to give us our y of x function, or our displacement function. And that's going to be 1 over EI times the integral of 0.35x squared plus C3 with respect to x. So that will be 1 over EI times 0.117x cubed plus C3x plus C4. And again, these are both valid for 0 to x to 4 feet, just like our moment function was valid. We've created 2 more constants from integrating, and so we'll need to develop at least two more boundary and continuity conditions, hopefully 3 more. 2 more to get rid of these 2 constants, and we still need an additional boundary or continuity condition to get rid of our constant above. We still have C1, C2, C3, and C4 to contend with. So for 0 to x to 4 feet, we have y at 0 equals 0, and that's because of our pin. Our pin at A will restrict any kind of vertical displacement. We also know that we have 2 continuity conditions here that will help us out. And a continuity condition is where you have a single point, and at that point you can apply either the equation that's valid to the left of that point or the equation valid to the right of that point. And using that, we can hopefully solve for a constant. So the term, or the variables, the notation I used in my class was y at 4 feet from the left is equal to y at 4 feet from the right. And also another continuity condition, we have rotation at 4 feet from the left is equal to rotation at 4 feet from the right. So the one that we've already plotted in the last segment, plus this one, and this one, that's a total of 4 boundary or continuity conditions. And so we've applied 1, let's apply these next 3. Start off by y at 0 equals 0. And if we do that, we have 1 over EI times 0 plus C4 equals 0. And so therefore C4 equals 0. Let's next try the continuity condition. Y at 4 feet from the left is equal to y at 4 feet from the right. Let's see where that gets us. So for this, we need to recall back what our final displacement equation was on the right segment, which was from 4 to 10 feet, and set that equal to what we just recently solved for as far as deflection that's valid between 0 and 4 feet. So we'll have 1 over EI times 0.117 times x, which is this case it's 4 cubed, plus 4c3, and I'm not going to put in a c4 because we know it's 0. So what I just wrote here, this is y 4 feet from the left, and we're going to set that equal to y at 4 feet from the right. 1 over EI times 0.117 times x cubed minus 3.5 times 4 squared plus 4c1 plus c2. And this is y at 4 feet from the right. We'll have to stop here, and I'll pick it up with part 2 of the same example next.